Hello friends, I welcome you in lecture number 16 on higher order partial differential equations. In this lecture also we will discuss one more problem on general method of finding particular integral of non-homogeneous linear partial differential equation with constant coefficients. Before going for this method, we recall the main formula of this method is that suppose we have 1 over d minus m d dash that we want to operate on the function say fxy, then we replace this y in fxy by c minus mx. This m is the coefficient of d dash here, and integrate with respect to x. If I replace y by c minus mx in this function of x and y, then resulting function is going to be a function of x only, so that I can integrate it with respect to x, and after integration I will put c equal to y plus mx. So this is the main formula for this method that we have to remember, and it comes from the solution of Lagrange quasi-linear equation that we have discussed in previous two lectures. Now we try to solve this equation. We are familiar with all these three notations. R, S, T are the notations for second order partial derivatives. R is the notation for second order partial derivative of function z with respect to say x 2 times. S is the notation for partial derivative of variable z with respect to x and y, and t is the notation for partial derivative of z with respect to variable y 2 times, or it is second order derivative with respect to y, equal to y cos x. We can write in the form of d and d dash also, as we know that d stands for partial derivative with respect to x, d dash stand for partial derivative with respect to y. Similarly, d dash square is the second order partial derivative with respect to y, z equal to y cos x. Now to solve this non-homogeneous equation, the first step is we have to solve the corresponding homogeneous partial differential equation. The corresponding homogeneous partial differential equation is, we have to consider right hand side equal to 0, d square plus d dash minus 6 d dash square z equal to 0. Now here we can observe that this is homogeneous function of d and d dash, so we can apply this formula. This formula is applicable if our function f d dash is a homogeneous function of d and d dash, and here this f d dash is homogeneous, and to solve this equation, first we have to replace d by m and d dash by 1 in this function of d and d dash and equate it to 0. That is, we have to write down the auxiliary equation corresponding to this. The auxiliary equation is m square plus m minus 6 equal to 0. Therefore m square, this m can be rewritten as 3m minus 2m minus 6 equal to 0. This I can rewrite as m times m plus 3 minus 2 times m plus 3 equal to 0. Therefore we have m plus 3 times m minus 2 equal to 0, and therefore m equal to 2 and minus 3, and we know that corresponding to each value of f, we are writing arbitrary function of y plus mx. Therefore, complementary function is arbitrary function of y plus 2x plus another arbitrary function of m equal to minus 3, so y minus 3x. Now we go for particular solution or particular integral. So particular integral is 1 divided by f d dash, which is d square plus d dash, d square plus d dash minus 6 d dash square operated on the right hand side, which is y cos x. So here we write y cos x. Now because this is homogeneous function of d and d dash, we can write it in the as the product of two linear factors of the form d minus m d dash, and values of m are 2 and minus 3. So here I can write, suppose I am writing for m equal to 2, then I have d minus 2 d dash, and for m equal to minus 3 I will have d plus 3 times d dash. This we have to operate on y cos x. Now we will use that formula which we have to remember. We will apply both the factors one by one to the right hand side, and for that we use this formula 1 over d minus m d dash operated on fxy is integral of f of x comma c minus mx, integral with respect to x, where we put y equal to c minus mx, so that we have function of only one variable and we can integrate it with respect to x, and after integral we have to replace c by y plus mx. So first we operate this factor to this function, and we keep 1 over d minus 2 d dash as it is. If we compare this with d minus m d dash, we can see m is minus 3, and we have to replace y by c minus mx, and m is minus 3, that is we will replace y by c plus 3x in this function. So there is only one y here, so that we replace by c plus 3x into cos x, and we integrate with respect to x, where y is nothing but c plus 3x. Now this is easy to integrate. We apply integration by parts by considering u equal to c plus 3x, v equal to cos x, and let me write that formula here for this u and v. So first we consider u as it is, that is c plus 3x as it is, and integral of v, which is cos x, integral of cos x is sin x, minus in derivative of first bracket with respect to x, which is 3, and integral of this sin x with respect to x is minus cos x. In the next step I have to write derivative of 3, but it becomes 0. So this is as it is, and after integration I have to replace this c plus 3x by y. So I am replacing this c plus 3x by y here, y sin x and plus 3 cos x. Now again I will apply the same formula. Instead of now m is different, m is 2. So now I have to put y equal to c minus mx, and m is 2. So now I will replace y by c minus 2x in this function, and then I will integrate it with respect to x. So y is c minus 2x times sin x plus 3 cos x integral with respect to x, where we know that y is replaced by c minus 2x, and here this I can rewrite as integral of c minus 2x sin x with respect to x plus 3 times integral of cos x with respect to x. Here we apply integration by parts. We consider c minus 2x as it is. Integral of sin x is minus cos x, minus derivative of c minus 2x is minus 2, and integral of minus cos x is minus sin x, plus 3 times integral of cos x is sin x. And after integration I have to replace c minus 2x by y. So here I am writing c minus 2x equal to y, and we have negative sign in the product, so we rewrite this as minus y cos x. Here I have product of minus 1 3 times, so I will have minus sign here, minus 2 sin x plus 3 sin x. 3 sin x minus 2 sin x is nothing but sin x and minus y cos x. This is particular integral. So this is very easy. We have to just replace this y by c minus mx in fxy, then we integrate with respect to x, and after integration we put c minus mx equal to y or c equal to y plus mx, and finally we write down the general solution. Therefore the general solution is z equal to complementary function plus particular integral, and therefore z equal to complementary function was arbitrary function of y plus 2x plus arbitrary function of y minus 3x plus sin x minus y cos x, and here phi 1 and phi 2 are arbitrary. So in this way we can easily apply this general method also, and the benefit of general method is that there is no restriction on the function on the right hand side. The only limitation is that here it is required that this function of d and d dash is homogeneous. If f d d dash is not homogeneous, then we cannot write it as a product of linear factor of the form d minus m d dash, and this method may not be applied in that case. So this is all about this session. I hope you like it. Thanks for watching.